Hello students, how are you? Today we are going to start a new chapter, electric potential and the capacitance. Now, the next chapter is the second chapter of your NCERT syllabus is electric potential and capacitance. But in today's class, we will devote the complete time of the class only to understand electric potential only. Will not touch capacitance, and of electric potential part also there are many questions we will be taking in a different session if time permits. Anyhow, in this session we will complete the understanding what electric potential is. So when we understand what electric potential is, we'll start with the work done. What work done is. Now we have some idea already regarding what work done is, because last year we had a chapter called work power energy, you remember. Now just to recall, if we have a body of mass m, let us say, and it is pushed in this direction with a force F, let us say, and whenever a force is applied on a mass m, this starts moving with acceleration a, or it tends to move. Now let us say this mass is moving and this has traveled some distance and that has gone to this position. This is the first position, this has gone to this position, and the distance between them is s, let us. Now since in the direction of the force only it is moving, the displacement s is equal to same as the distance displacement, not much difference here. Now we know this is a repetition. You remember last year you had studied this thing. I am going to relate the work done concept with electric potential, that's why I am just recalling it. So W was equal to F dot S is equal to F dot S is Fs cos theta, right? Fs cos theta. Now what is the theta? Theta is the angle between F and S. Now F also is in this direction only, and displacement also is in this direction only. So F, S are in the same direction, implies that angle between them is 0 degree, isn't it? So cos 0 is equal to 1, we know. So this is simply Fs, implies that W is equal to Fs. So as long as the force, since theta is equal to 0 degree and cos 0 is equal to 1, so you put it 1 here, so W is equal to Fs. So as long as the displacement is along the applied force, we are always safely, we can take W is equal to Fs, as simple as that. Now why I am saying what is electric, what is the work done? Now this is the concept what we have learned from last year. Now let us say this entire thing was rough for today's class. Now let us see what is electric potential. In electrostatic, if there is a charge, okay, and there is an electric field inside which the charge is moving, there is one electric field inside this, the charge is moving. Let us say charge is moving from one point to another point B. Then it is moving in any path, let us say like this, or maybe it is moving just like this, or maybe it is moving just like this. In any path it is moving. If the charge is moving from one point to the other, if the points are fixed, the work done is same. How we are going to see? How we are going to see mathematically, but the work done in moving a charge from one point to another is the electric potential energy. Electric, for potential energy I am writing PE. Electric potential energy is the work done. So electric potential energy, we'll see. Okay, we were calling that the work done only is called energy. This concept also we remember from last year only. Okay, now where I said, I repeatedly I said, took the same example that if let us say there is a table and you have a duster, and the height of the table is h, let us say. The height of the table is h, let us say. Mass of the duster is m, let us say. Now you lift it and you keep it here. Now mg was the force with which the earth pulls the duster. Against that force you are applying a force which is equal to mg, that's why you are able to move it, and height h you remove. So what work you have done? mgh work you have done, and when you kept it, it is not able to move down, so that work stored is energy. And I said exactly these words: work stored is energy, and energy spent is called work. That means if I remove this duster and I simply drop, that will come down. So work is being spent in moving it. Work spent, energy spent is work, and work stored is energy. As simple as this. So mathematically or numerically, work done is same as energy. Now that work done when a charge moves inside one electric field from one point to another is electric potential energy. Now this is electric potential energy difference. Now when instead of a Q we will imagine a unit positive charge, we will call that electric potential. In some time we are going to see that in a detail. Now one more thing, I'd like to give an analogy, mechanical analogy, because electric field also is something you cannot see. Electric charge also something you cannot see. Electric charge is moving, something invisible is moving in something invisible. So it becomes a little tough to understand, right? Now we will compare this with some analogy from day-to-day life or some mechanical example, let us say. We are having a structure like this, let us say. And this side also there is some water to a bigger height, and this side there is same water to a smaller height, and if it is open then the height will be balanced, right? But in between, let us say there is a stopcock, as let us say this column is A, this column is B. The water is there. Now if this stopcock is removed, then water from A column will go down and the water column along the B will rise up, and both the levels will be equal, right? Now where else you saw this kind of a thing? You remember, if heat always flew from hot body to cool body, so what was the difference which measured from which direction to which direction it will flow? Now see, in case of water, from higher level to lower level it flows. Higher level to lower level. In case of heat, it flew from higher temperature to lower temperature. You remember, always heat never flew from lower temperature to higher temperature unless some external agency does some work on it. So that thermodynamics, we studied those things, right? So heat is a similar thing which always flew from a higher temperature to lower temperature, transferred. Water is being now in this example higher level to lower level. Exactly similarly in electricity, higher potential to lower potential, always what will flow? Charge will flow. Charge will flow from higher potential to lower potential if it is free to do so. And when we say charge, we imagine plus charge only, and this side is a plus side and this side is a minus side. This is a pure convention. Whenever I am teaching, I am saying like this only, but you may consider plus this side, minus this side, that doesn't matter. And if you take minus also charge, that doesn't matter. We have to be concerned, we have to be careful what is the sign of the charge. But just to understand from the basics, I am always taking plus charge only, and this side is the plus side, this side is the minus side. I am taking like this, so that the direction of electric field is always towards the east. Now mathematically we are going to see how electric potential is the work done. Mathematically we are going to derive that thing. Now let us say there is one electric field, and knowingly I am taking one non-uniform electric field, because if non-uniform electric field, it is true for electric field also, for uniform field also it will be true. So let us say there is a point A and there is a point B inside this non-uniform electric field. Okay, now let us say this moves like this to B. A charge, this means what? A plus charge, plus one charge, let us take from the beginning, plus one charge moves to B. Now what is the work done? Now see, imagine a simple structure, E is in this direction, and if a plus one charge is moving, what you will do? Let us say it is moving by a small length element dl. Then the force multiplied by the displacement is the work done. Now dw will be equal to force multiplied by dl, let us say. dl is the length element we are taking. Now F is what? Since we have taken a unit positive charge, the force on a unit positive charge is electric field intensity. We have said that already. So F, force on a unit positive charge, itself is electric field intensity. Now E is in the same direction of a dl. So we can say this as a simply EDL, because EDL cos theta between E and dl is 0, cos 0 is equal to 1. So dw is equal to EDL, implies that W, total work done, is equal to E dl from A to B. Is it clear? It's very clear, simple, right? So this, and why we did this integration, it is because this is a continuous path and it can be anything, as I said you, right? It can be like this also, it can be like this also. So in any path, any continuous path it is going. So instead of, otherwise what is the integration? We are finding out EDL for a small dl1, let us say. It is dl2, dl3, dl4, dl5, dl6, like that. So many dls till b we are adding. Then what we are doing? W is equal to E dl1 plus E dl2 plus like that, all the dls we are adding. So finally we are finding, actually we are finding the EDLs from A to B. Everything we are adding up, and the mathematical technique for that is integration of E dot dl, and in this case EDL, because E dl are in the same direction. EDL from A to B is equal to, what is EDL? What is E? 1 by 4 pi epsilon naught q by, okay, we will go into the mathematical calculation after, but EDL integration A to B is the work done. Now this work done is called a line integral of electric field, line integral of electric field intensity within two limits is the work done in moving a unit positive charge from initial point to final point, and this itself is called the electric potential. And what is the symbol of electric potential? We will take a V, and V, since it is a work done is a scalar or vector, it's a scalar, so it will be a scalar quantity. You remember last year we were taking small v for velocity and capital V for volume, like that we were taking in chemistry, but now going forward you be familiar with this symbol. V, capital V will be taken for electric potential. This is what? Electric potential at A minus electric potential at B, right? So this is change in V, that is V at A minus V at B. So VA minus VB. Electric potential at A minus electric potential at B is VA minus VB. That is also sometimes written as VAB. And that is what? The potential difference between A and B. It's called also potential, electric potential difference. Potential difference also we will be calling it most of the time. We will be not using the electric word, but electric potential difference between A and B is written as VAB, which is equal to the work done in moving a unit positive charge from point A to point B. Now, a fundamental question remains, what is the work done if I move the charge from A to B? If I move in a different path, Why the work done will remain same only? Why it is not different? The starting point is A only in every case and the ending case is B only in every case. But how can you be sure that it is same only? Numerically it could be different, it may be different. Now let us see. This is basically what E dot dl, right? E is a constant. Now E dot dl when we say it is a vector quantity. Now you remember, if A to B, all dl's we are adding here, right? So if we take E common, dl1 plus dl2 plus dl3 plus so on, right? And all are vectors, right? Now to be accurate, now dl1 plus dl2 plus dl3 till all the dl's if we add till B, what will happen? Don't you think that that will be the length of the shortest distance between A and B? Now let us say I am showing it here. A is here. Okay, I have showed it already. A is here, B is here. Now if you move a unit positive charge along this path, then what will the work done? E dot L. L is this much. L and the direction is this one. Now if you take the unit positive charge from A like this and you bring here, so E into this much L plus this much L will come, right? Now triangle law, you remember, this plus this will be equal to again AB only, right? So if you are bringing like this, then from here to here like this, and then again you are coming. So again this vector plus this vector plus this vector is the same as AB vector only, right? So in whatever path you travel, let us say you travel this way, this way, this way, you are taking a unit positive charge, whatever path you follow and bring it to B, then this vector plus this vector is this vector, and this vector plus this vector is this vector, and this vector plus this vector is this vector, and finally this vector plus this vector is again AB only. So this is a purely vector concept, that when we are adding the vectors all together, that is always a vector of a magnitude, the shortest distance between the initial point and the final point, and the magnitude is the shortest distance between them. And that is why whatever is the path followed, if the unit positive charge is taken from A to B, the work done will be this much only. EDL integrated within the limits A to B only. So clear? Theoretically you should be very clear, so that later on when we deal with some numericals etc., we will be applying these concepts again and again. Now we will be deriving electric potential at any point due to a single point charge. Due to a point charge, electric potential at any point due to a point charge. Now listen carefully this concept. Let us say we have a charge Q here, and due to this we are going to find out the potential at a point P here. Let us say, let's give some names. This point is O, this point is P. So and the distance between OP is R. So we are going to find out the electric potential at any point P at a distance of R from a point charge Q. Okay, to do that, what is the electric potential? By definition we know now that the work done in moving a unit positive charge from infinity to point P. Let us say this is a positive charge. Now if we will move one unit positive charge towards it, this, as we bring it near and near, this Q will push it, because both are like charges. Still, if we are bringing it nearer and nearer, we have to do some work. That work done in moving a unit positive charge from infinity to point P is called the electric potential at any point due to that point charge. Okay, now so wherever that point is there, along that line only we are discussing. Let us say that point is now somewhere, that point is somewhere it is at A. You imagine one unit positive charge at A. So from infinity we are bringing it to P, and we are going to see how much work is done. Now from infinity we are bringing it. Let us say from point A to point B we moved it by a small distance dx. Now what we'll do is, what is the work done in moving it from for this much distance, and then we will integrate that within the limit infinity to r. Clear? From infinity to r, how much work will be done, that we are going to calculate. And what is the integration technique? We are considering a small work done in moving the charge from A to B through dx distance. How much work done we are bringing. So let us take some assumptions. Till A is any point, or x is the variable. Let us say that is at any distance x from the Q now. And from there, just to move a little distance dx, what is the work done, that we are calculating? dw is equal to, let me write in black only. dw is equal to the small work done in moving the unit positive charge from A to B through a small distance dx. What is the work done? The force on that unit positive charge. Since force on unit positive charge is electric field only, so what is the electric field? E dot dx. Now since this is displacement, I am showing the vector mass, and the dot product of two vectors is a scalar of course, equal to E dx cos theta, where theta is the angle between E and dx. E is 1 by 4 pi epsilon naught q by x square multiplied by dx. Then cos theta. Theta is what? Angle between E and dx. What is the E direction? From positive it is going away, right? So this is E direction. What is x direction? The displacement is happening in this direction, we are bringing it. So dx, this is in this direction. So what is the angle between them? 180 degree, right? So cos 180 degree is equal to minus 1. So we can bring minus 1 by 4 pi epsilon naught q by x square dx. But this is dw. What is the total work done in bringing it from infinity? Bringing it means bringing a unit positive charge from infinity to this point is called the electric potential at any point due to a point charge, right? So therefore the total work done is equal to integration of dw from 0 to some w. This is the mathematical style of writing, but this is integration of E dot dx within what to what? Infinity to r. Infinity to r. Is it clear to everybody? From here, is it visible? From here I am writing it here. From here I am continuing. Therefore work done is equal to, see, E dot dx. This one we are writing, this we will be keeping in integration of dw from infinity to r. This much is equal to integration of dw is equal to how much we brought? Minus 1 by 4 pi epsilon q by x square dx. Now q 1 by 4 pi epsilon naught, all are constant, so I took out of, minus sign also is constant, I took out of the integration sign. Okay, let me write first minus 1 by 4 pi epsilon naught q by x square dx infinity to r, right? So this is equal to, you take all the constants outside, minus q by 4 pi epsilon naught integration of 1 by x square dx infinity to r, right, is equal to, now what is the integration of 1 by x square dx? Isn't it minus 1 by x? You pause, you see it for yourself. I am not explaining that integration part again. Many a times I have explained already from the last year also. So minus q by 4 pi epsilon naught, and this is minus 1 by x, right? Infinity to r, and this minus is a constant again, you can take it out, so minus minus become plus, is equal to q by 4 pi epsilon naught 1 by x between the limits infinity to r. Now for x you put r first, 1 by r minus 1 by infinity, and 1 by infinity is 0, therefore w is equal to 1 by 4 pi epsilon naught q by r. Is it clear? If you want me to write it separately, okay, let me put it. For x r you put 1 by r minus 1 by, for x I put infinity. Now 1 by infinity is 0. So 1 by r minus 0 is 1 by r only. But the work done in moving a unit positive charge from infinity to r is called electric potential at any point due to the point charge. Therefore, and the symbol of that is V. So this work done, or that only is called V, is equal to 1 by 4 pi epsilon naught q by r. Is it clear to everybody? Now, potential difference between, this is the potential, electric potential at point P. But what is the potential difference between A and B? Potential difference between A and B is equal to VA minus VB potential at VB minus VA potential at B minus potential at A. What is the meaning of why I changed this thing? Now you tell me whether the potential at B is more or potential at A is more. What is potential we have learned now? You tell me what is, okay, in a video session you cannot respond. Anyway, the potential of a B will be more than potential of a A. Is it clear? When you bring till B, it will be more pushed by this charge because B is nearer than A, right? So VB minus VA. So if I write it here, VB minus VA, what is VB or VA? What is V? We have calculated already. So I'm just erasing it. You have this picture in mind already. So to make a little space, I'm erasing it. So this is equal to 1 by 4 pi epsilon naught. Q is there, right? And Q will be here also, there also. So Q by 4 pi epsilon naught 1 by RB minus 1 by RA, where RB is the distance of a B from O and RA is the distance of A from O. Or in different vectorial language we can say RB and RA are the position vectors of B and A respectively. So fine, potential is equal to 1 by 4 pi epsilon naught q by r, and potential difference is 1 by 4 pi epsilon naught q by r1 minus 1 by 4 pi epsilon naught q by r2. So 1 by 4 pi epsilon naught to q, if you take out 1 by r1 minus 1 by r2, or 1 by rb minus 1 by ra, whichever is bigger minus smaller. Now there is only, because of terms there is a little confusion, like electric potential, and there is another term called electric potential energy. What is the difference? Let us see. See, electric potential, we said that the work done in moving a unit positive, electric potential at any point due to a point charge is 1 by 4 pi epsilon naught q, that point charge, magnitude of that point charge, divided by r. This is electric potential we have calculated already, and we wrote that also as V. It is electric potential. Now there is another term called electric potential energy. Now see, what is electric potential energy? The conceptually it is same only, but when we calculate what is electric potential, the work done in moving a unit positive charge from infinity to a particular point. Now, instead of taking a unit positive charge, if we will take any charge q naught, let us say a test charge, anything other than it's not only unit positive charge, any charge if we take, then what will happen here? Q into q naught will come, right? Instead of q into plus 1 was there, that's why nothing was there. Now one additional q naught will come, right? So if v is equal to 1 by 4 pi epsilon naught q naught by r, then we will call it electric potential energy. And if that is only 1 by 4 pi epsilon naught q by r, we will call that electric potential. That's the difference only. So electric potential multiplied by the charge which is carried is called electric potential energy. So electric potential energy for any charge being brought from infinity to a particular point is same as, instead of any charge, if we take a unit positive charge, that only given a name electric potential. That's the difference. So mathematically speaking, calculate the electric potential energy when we say RV will be 1 by 4 pi epsilon naught q, and that whatever is the charge divided by r, and this is energy, and electric potential will be 1 by 4 pi epsilon naught q by r. Here instead of a q naught we took a plus 1, so q multiplied by 1 remained q only, that was divided by. Hope the concept of electric potential at any point due to a point charge is clear, right? Now related to this, one more concept also is exactly similar to this, only nothing new. Electric potential at any point due to, instead of one point, due to multiple charges. Then what will happen? Let us say we have a charge q. Due to this, at point P, what is the electric potential at any point at a distance of r from it? We are able to calculate now. That is equal to 1 by 4 pi epsilon naught q by r. Now, suppose there is another charge. Let us say this is q1, q2, there is another charge q3, and many charges are there. What is the electric potential at point P due to all these charges? Then that is, since this is a scalar quantity, here there is no vector also, it is simply algebraic addition of the electric potentials due to all these. So what is the electric potential at point P due to the multiple charges? Is equal to the electric potential, sum of the electric potentials at point P due to individual charges. That means, let us say it is V1 is due to Q1. Potential at a point P is equal to V1, where potential at point P due to Q1 charge, plus V2 plus V3 plus so on. So if we write it mathematically, V1 is equal to how much? 1 by 4 pi epsilon naught Q1 by R1. Let us say from Q1 the distance is R1, from Q2 the distance is R2, from Q3 the distance is R3, let us say. So here 1 by plus V2 is 1 by 4 pi epsilon naught Q2 by R2. So 1 by 4 pi epsilon naught is common everywhere. So Q1 by R1 plus Q2 by R2 plus so on, right? So this mathematically is written as combinedly, therefore V in general is given by V is equal to 1 by 4 pi epsilon naught summation of Qi by Ri, where I is equal to 1 to n. This is electric potential due to a point charge at any point due to due to multiple charges. Clear everybody? So going further, the coming session will be a continuation of this, but we will be going into the concepts and related numericals on which questions are being asked. Today's session was only to make you understand about what is electric potential, what is electric potential energy, and how it is nothing much different from the mechanical idea of work done. So hope this session remained fruitful. Thank you everybody.